the last class we were talking about the point defects, and we showed that they were in thermodynamic equilibrium, and moved on to the line dislocations, and we saw edge dislocation. Whenever any plane is not complete in the crystal, the internal edge of the plane forms an edge dislocation. Today I am going to talk more about this edge dislocation and try to generate a dislocation in a perfect crystal. But before I begin to do that, I just want to remind and give a caution that this is not the way anybody can create a dislocation in the crystal. I am just trying to do something to convert a perfect crystal into an imperfect crystal with an edge dislocation. Thereby I intend to define a few terms which we shall continue to use with reference to these dislocations. But keep it in mind that you cannot do these things to create a dislocation in the crystal. Right. Here I show a crystal where the vertical planes, if you want you can number these, they are complete, go from top to the bottom, and this is, let us say, a simple cubic crystal. In the middle of the crystal I have sketched another plane. Let me name this plane A, B, C and D. All the planes 1, 2, 3, 4, 5, 6, they are all complete from top to the bottom. And I have taken a plane or horizontal plane in the middle of the crystal. On this plane there are atoms above the plane, below the plane, like this. They are there in all of them and they are bonded like this. What I do now is, for the atoms which are above the plane and below the plane, in between I break these bonds or cut these bonds in a certain region. Let us say that region in this place is and name this as E and F. So A, B, F, E is the region on this plane A, B, C, D with a very thin narrow blade which is a fraction of an angstrom thick. Obviously you can see that you cannot have it. We cut all these bonds which are lying on this. So they will be on these three planes which I have shown here. These bonds are broken or cut. After I have done this, all the bonds are cut. Top part of the crystal I push with reference to the bottom part of the crystal with a force, so that this first plane is shifted on this place by one interplanar spacing, by that much distance. I pushed it hard. After I have done pushing, just introduce some glue in this region and allow the bonds to form again, right, and see what happens when I do that. This is what happens when I allow these bonds to form. This is your plane number 1. This is number 2, this is number 3, 4, 5 and 6, and I cut the bonds between these 3. So what has happened when I pushed this one on top, number 1 has gone bonded with number 2 on the below this plane. This is the plane where I had cut the bonds, and this one got pushed to the third one. Number 2 got pushed from the top to the third one, but the third one does not get pushed to the fourth one because this bond is not cut, and therefore this plane hangs here and is unable to form the bond there. I have formed a part plane in the crystal by this technique. Alright, and this is the configuration of an edge dislocation. In here you can also see these bonds are compressed while this bond is extended. While I go away, the bond length becomes normal bond length. They go away, the bond lengths become normal, but here these are compressed. So above this plane where I cut the bonds, these are compressed, and here they are extended. So there is tension here, there is compression here. That's what we showed in the last class, but this is what you see here. When I do this, that's done. By doing this, what have I done is I have introduced a few things. What have I introduced is, now the way I did things, I introduced this plane A, B, C and D, and on this plane define this E and F. So this plane A, B, C, D over which the crystal has slipped, I made it to slip. So I call this plane A, B, C, D the slip plane. On the slip plane, this part A, B, F, E on which I pushed these atoms, because I had cut the bonds earlier and then made the bonds again, I call it the slip part of the crystal. And this C, D, E, F is called the unslipped part. But you notice that slip is a relative term. If I call this as the unslipped and call the slipped, that as the unslipped, somebody can call that as the slipped and this as the unslipped. Because this is the way I showed it, is you cannot create a dislocation. It comes about in some other way. Those things we'll see later. But these are relative terms, whether this part of the crystal has slipped with respect to that or this has slipped with respect to that. So the whole plane, slip plane, has two parts. One is a slipped part, other is unslipped part. And this line EF is a boundary between the slipped part and the unslipped part. And what is this boundary? It is the edge of the part plane. And edge of the part plane is what I call the edge dislocation. So this EF is the dislocation. Where this line EF lies? It lies on the plane A, B, C, D. there is a slip plane. So these are some of the terms which I have introduced, right, and we shall now define a dislocation on the basis of what we have understood here. Well, that's what you see. This is your.
Yeah. Can you tell in the lower part why there is tension? There should not be anything.
Why is there tension?
In the lower part.
See, this is why I said that I will first cut the bonds here, push this one, so I am squeezing the top part anyway, right, and allowing this to form the bond with this, and I have joined it with the glue or something. Let us say bond is formed. The bond is formed here. Notice here in this space I have more planes, and in this space I have less planes. Obviously that has to be adjusted. You squeeze the top part only. It is also relative. You can say that you have pushed the top to the right, you can say that you have pulled the bottom to the left. So that way there is going to be a extension here, because after all the space is the same in which all these are arranged, all the 6 planes are arranged, right. So therefore there is a compression here in this region, and there is tension here in this region. So I define now a dislocation is a boundary between the slipped and the unslipped parts of the crystal that you have seen and lying over the slip plane. I first created the slip plane with the push to the top part of the crystal with reference to the bottom part, not over the entire plane, only part of the plane. So that forms a boundary between the slipped part and the unslipped part, and wherever the boundary is, I got the edge dislocation. Is the meaning of this sentence clear to you? Good. If the meaning of the slip part, unslipped part and the boundary of these regions is clear, then I have to say about the extent of slip. While trying to create this dislocation, I said I will push the top part by 1 interplanar spacing, so that my atoms of the first plane go to the second one in the bottom, right. If that is clear, then direction and magnitude of this is called Burgers vector. Now, as I said already, direction is relative. When I said top part is pushed to the right like this and bottom to the left, it is relative. So, we determine the Burgers vector of a dislocation line by using a technique what is called drawing a Burgers circuit. Burgers circuit is nothing but a circuitous path in a crystal. Okay. And this circuitous path passes through only the perfect parts of the crystal, not through the imperfect. Imperfect part here I am referring to, I just showed you an edge dislocation. Around that the bonds are strained. Above the slip plane they are in compression, below the slip plane they are in tension, not through this region. Dislocation should not, the Burgers circuit should not pass through this region. Perfect parts where the bonds are not strained. Okay, so it has to go away from this region, but it is a circuitous path, and the net displacement along the path is 0. That's another important feature here, that the net displacement along the path is 0. Well, we will demonstrate that, what I mean by this. The Burgers vector is then the closure failure of the Burgers circuit. We'll come back to there. All right. This is the dislocated region here, and this part, let's say, bonds are not strained so much as I go away from this. So maybe I can start somewhere here, let us say, sorry, to sketch a circuitous path. Alright, before I do this, let us put a circuitous path in a perfect crystal. That would be better. Let's do that. Alright, that's the one. In this, okay, let's try this. So I made it all the unit cells, let us say. I start at this point P and draw the circuitous path. Let us say I go clockwise. I reach at this point here. How much distance have I traveled? If I define my A axis and B axis, it will be easy for you to do that. Let's define this as the A axis, that is the B axis, and this is the C axis. How much distance have I traveled? I have traveled 1, 2, 3, 4, and this is positive of A, right? And let's travel this way. How much have I traveled now? 1, 2, 3, 4, 5 and 6. So I have traveled on C minus 6. Right, travel here 1, 2, 3, 4, 5, and I travel minus 5 on A. Right, 1, 2, 3, 4, and reach here. Got plus 6 on C. Well, that's still not close, so I have to make it 0. I go here, we had plus 1. So I start at P and end at P. There's the same point. Starting point and end point are the same. This is 0, this is 0. Now my Burgers circuit is complete. So when I have drawn this in a perfect region, the Burgers circuit has closed on itself because the net displacement of the path is 0. I'll just show this now in my edge dislocation, what happens. Alright, let's start at this point P. On A, how much have I traveled? 1, 2, 3, 4. So I traveled 5. This is C, let us say. I have traveled minus 5. So I have traveled up to here. So let's go up to here only. Let us see. This is 1, 2, 3, 4, minus 4 on A. So A is closed. 1, 2, 3, 4 and 5 plus 5. Net displacement is already 0. Both A and C have become 0. But I end at Q. I started at P and ended at Q. Now the circuit has not closed despite the fact the displacement along the path is 0. So what I have to do is I have to add some more movement to make it close, and that movement which I have to make is Q to P. So this is the magnitude and displacement or the direction becomes the vector which I call the Burgers vector of the dislocation line. Right? This is the Burgers vector of the dislocation line which we have found out. It gives me the direction and magnitude both. This is the magnitude by which I had caused the displacement, caused the slip, and this is the direction in which I caused the slip, that you remember. However, this is what I did to the top part, displaced it to the right by 1 interplanar spacing. If my friend decides that I do not want to go clockwise, I would like to go anti-clockwise, he starts at Q, goes along, makes the net displacement 0 and reaches at point P. Now to close the circuit, he will have to add P to Q, not Q to P. Magnitude is alright, but the direction has changed. And this is an obvious ambiguity. Why it is obvious? There are two parts, one above the slip plane, one below the slip plane. Top part is given push to the right, in other words, bottom is given a pull to the left. The reference is what? Depending upon what is my reference. If I have taken my bottom as a reference, I have found out displacement on top, that's correct. If you take top as the reference, find out displacement at the bottom, you will get the opposite. So we settle this ambiguity once for all by saying that Burgers circuit is drawn using a right hand screw notation. What is a right hand screw notation? For the right hand screw notation, the first thing is I must decide the direction of the dislocation line. In this case, my dislocation line is right here, going inside. F point, E point, they will be visible at just one point here. It's a line inside the crystal. Okay, front is F and the back is E. So whether I take the direction of the dislocation line E to F or F to E, it is arbitrary and left to me, left to the user. You can choose the dislocation, it's a line, dislocation is a line, nobody has shown it as a vector in the crystal. Direction, once you give to it, it becomes a vector. That's called the dislocation line vector. So let's take from F to E. So if I take it from F to E, that is going inside like this, the dislocation line, which we represent by a vector T, let us say, which is here, just a point here, this F to E. Then the right hand screw should be moving in, I should rotate this, or the direction orientation of the Burgers circuit should be such that right hand screw goes in the direction of the dislocation line. Right hand screw will go from F to E if I go clockwise. If I go anti-clockwise, it will come from E to F. So right hand screw notation says I must have the orientation of the circuit such a way that if a right hand screw is rotated in that orientation, it will go in the direction of the dislocation line. In my case, dislocation line is going from front to the back because I have taken the direction F to E. Is it clear? Alright, so I must draw a clockwise circuit. Then this is my Burgers vector. That I am finding out what is the displacement given the top part with reference to the bottom part. Is this clear? Alright.
Then the direction of the Burgers vector will be determined by the choice of that edge dislocation vector.
T vector, yes. It will depend upon that obviously then. We shall see that what it results in actually. So we were here, Burgers vector is the closure failure of the Burgers circuit, and there is a natural cause for ambiguity as we discussed, right? And to avoid this ambiguity, we use the right hand screw notation in drawing the Burgers circuit. That's what I explained just now. Then I have no ambiguity. Alright, let's see what it results in. I had taken, let us say this is my slip plane. Alright, we have chosen the direction I'm sorry again make I think we chose the direction F to E. Okay, so this should be this is my T vector, and we found the Burgers vector from Q to P like this. All parallel vectors, wherever you draw the same name we give them. So this is the Burgers vector we find. Let me ask a question. If I had chosen the direction of the dislocation line which way shall you draw the Burgers circuit? Anti-clockwise. On the front plane you are drawing, and what will be the Burgers vector? Opposite to this, from P to Q instead of Q to P. I say whether you have chosen the direction of the dislocation line F to E or E to F, you have got the consistent result. What is the consistency here? Angle between B and T, that is B to T, is 90 degrees. Define the angle like this. From B to T, the angle you define is 90 degrees. And if you look at the vector, if I talk in Cartesian geometry, let us say this is a simple cubic system where I can talk of the Cartesian geometry. look at the vector B cross T. Which way does it point?
Out of the plane.
Out of this plane, but in the crystal, if this plane is the slip plane, which way it is pointing in the crystal?
Vertical. The C direction.
Above the slip plane ABCD, it points above the slip plane, and that is the side where I have the part plane. Not the dislocation is on the slip plane. Dislocation is on the slip plane. It points in the direction in which I have the part plane, whether I take this or I take that. That's why I mean, when I say this result is self-consistent. So it is a material which direction you choose for the dislocation line. Is this clear? Whether you take from E to F or from F to E, it's left to you, but you must draw the Burgers circuit using the right hand screw notation. Then you will get the right kind of a Burgers vector. Now in the edge dislocation which we have shown, the symbol I use to represent this dislocation which I just showed you, the part plane coming from the top and there is a slip plane at the bottom on which it stops. It's an inverted T basically. So this is the part plane and this is the slip plane. There is a symbol we use, and in here we have seen the relationship between B and T. Angle is 90 degrees. This is B, this is T, and this angle is 90 degrees. B cross T points upwards. So relationship between B and T. Such a dislocation is called positive edge dislocation. This case, I gave the push to the top part to the right. Instead, I had given the push to the left part to the right. Sorry, the bottom part to the right. Instead of top part to the right, I had given the push to the bottom part to the right. Or in other words, I had pulled the top part to the left. What would have happened?
The direction of B will be changed.
No, what would happen to the structure when I do that? Where would the part plane be if I do that?
In the bottom.
Below the slip plane. We have understood this? The part plane would be below the slip plane if you do that. That means the whole configuration is upside down.
Yes.
Configuration would become upside down. Part plane is below the slip plane. In such a situation, we write the symbol like this. This is the part plane coming from the bottom and stopping at the slip plane. In this case, when you find out B and T, if you take the T vector like this going inside the crystal, you will get the B vector like that. Angle between B to T will be, you will find 270 degrees, not 90 degrees. I am working out from B to T, right? And this is called a negative edge dislocation. Now, why there is a need for me to call something positive, something negative? Because when I turn it upside down, it's become positive, negative. If it was negative, it becomes positive. but the positive would become negative, because in a crystal I could have two things existing together, one with a configuration such that the slip plane, part plane is coming from the top, the other one is there with the slip plane here and the part plane is coming from the bottom. They are existing together. Strains in one are opposite of the strains in the other. Therefore, why is a need for me to call one as positive, other as negative? More we shall understand when we start to see when the dislocations begin to move, they come together, come towards each other, go away from each other, what happens? We will come to there when we talk about it. Right. Now this is, I have shown three-dimensional crystal, solid crystal, simple cubic again, the configuration of a dislocation, edge dislocation. This is that part plane which stops here, and this is a, as shown here, is a positive edge dislocation. Coming from the top, stopping at the slip plane, which I have shadowed yellow here as the slip plane, right? And see, number of planes in the top, number of planes in the bottom are the same, they are not different, but in here there are the same number of atoms are squeezed in this one planar spacing less. That's why you see these are in compression while these are in tension.
So are the number of planes same?
Yeah, you can see that. I started with the perfect crystal, cut the bonds here, slip the top part to the right. Now I've got the configuration. If I allow it to come or forward, push it, maybe this goes out. And then it becomes a perfect plane crystal. See, number of planes you can count: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Count here also: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's the same. It's not different. Is this clear? Well, that's an edge dislocation in the crystal. And you can draw the Burgers circuit, you will find the Burgers vector turns out to be equal to this push which you are given here. That's what I just now explained, that though the choice of the dislocation line vector T is arbitrary, you take it from E to F or you take it from F to E, the notation, right hand screw notation, leads to a consistent result. Well, I just now explained this positive edge dislocation and the negative edge dislocation. That's the positive one, T and B, or you can have T like this, then the B will be like this. Negative edge dislocation is this, where T is this way, B is this way, or you can take the T this way, then the B would be this way. Right, that's the angular relationship between P and T. And this is, as I said, the Burgers vector is an important characteristic of a dislocation line. Particularly in an edge dislocation line, Burgers vector is at 90 degrees to the dislocation line. 270 is also 90, perpendicular. So Burgers vector is perpendicular to the dislocation line. That's an important characteristic of the edge dislocation. Okay. Next problem, we will try to see the another straight line dislocation. which is a screw dislocation. This is another straight line dislocation. Okay, right. Let's come back to our perfect crystal with the vertical planes shown there. Now what I do is, on the slip plane which I named A, B, C and D, let's make the slit which I said I'll cut the bonds cross, name this as G and H. Let's cut the bonds on this slit now, on this part of the plane, that is BCGH. This we cut the bonds, give the top part again a push by one interplanar spacing, but in front. The back, since you have not cut the bonds, you will not be able to do it, but in front you can do it. Push them so that this atom which is bonded here will go and bond with that. Okay, like that will go on, and once you have done this push, let's see what happens to the configuration after give this push and allow the bonds to form again. What happens? We get a configuration like this. I tilted it to show you what is going to happen here. It's up to here I have cut the bonds. Beyond that bonds are not cut, so this atom on here is bonded to that atom without problem. But this bond is cut, so this is pushed. But it cannot be pushed as much as the front one can be pushed. So I have been able to push this by almost one interplanar spacing, while these go for fractional part distance, because this one doesn't move at all, because bond is not cut there. So some kind of shear is taking place in the crystal.
But in this case, edge dislocation doesn't appear because we have cut through the plane.
Yeah, we have cut this. There's no edge. There's no edge here. There's no edge here. Well, what I'm going to show what it is there, you will see that. So this is the configuration which I have got. This is got bonded with the next and like that. And you notice here, you don't see any problem with the crystal. It's a perfect crystal. Every unit cell is a square, no distortions. Distortions are only here in this part. But if I look at here, each one of them is a square, but maybe it is slightly tilted with reference to these squares. This is some kind of a shear has taken place here, and a shear has taken place in this region. As I go away, these trains will also not be visible. I have shown it purposely here just to demonstrate that something is happening. But when I go away some 10-20 planes, I will not see those trains. Depends also upon the nature of the bond. If nature of the bond is very flexible, a very metallic kind of a bond, it may go beyond 10 planar spacings. But if it is a partial covalency is present, then it will not go very far off. So these trains do not go away very far, but they are visible around here very much. Now let's see what has happened. After giving this push, the border or the dislocation line is here. This is the H point and G point is on the other side. That is the dislocation line. But around the dislocation line, what has happened? Just see that I start from here, this corner, top left corner in the front, and I go backwards inside the crystal and then come down and move like this. I have come here and I try to move. Well, this is continued. I am going out onto some other plane, not on the, I started here. I will never reach there. In other words, if you start from here, go in a clockwise fashion. I went in anti-clockwise fashion. Go in the clockwise fashion. You start here, go in the plane below, reach here, come there, reach here, go to the second plane there, reach here, go there, go to the third plane there, reach here. See, you are able to go inside the crystal. But you try to do this here, you keep moving on the same place. You do it here, you do it here, you do it there. These are called the perfect parts of the crystal. Anywhere in the perfect, well, here if you do, no problem, you will be there only. You shall keep moving on this plane only. But only when you enclose this region, which is the GH line in your movement, that you are able to go inside the crystal. As if you are going on these spiral stairs. You know, you have seen these stairs, these kind of spiral stairs in IIT are there, number of places. Go like this, going along the central line. So that is why it is called a screw dislocation. And like a clockwise or anti-clockwise motion of the screw, it is either going inside the crystal or going outside the crystal. That's why it is called a screw dislocation. All right, let me take my dislocation line is from G point, it is going inwards to H. H is somewhere there, let us say. It's going in. I'm sorry, I think I earlier wrote G on the other side. All right, let's rub this off. I wrote G on this point and H on this side. So my T vector is from H to G. That's my T vector. With this T vector, which way should my Burger circuit be drawn, clockwise or anti-clockwise, so that right hand screw rotation moves inwards? Clockwise. So let us start in this plane at this point P. Right? Once again, let us define our direction vectors. Let me run parallel to this crystal itself. Let's call this is A axis. This is my B axis, and that is my C axis. B is slightly tilted, or it doesn't matter, we will know what it is. So I go in this direction. This direction is B, and how much have I travelled in B? 1, 2, 3, 4 and 5. Then you can go how much have you travelled here? 10. And this is C. Now that's my direction, okay, of motion. How much is this? 1, 2, 3, 4, 5, 6, 9, 10 again, okay. And this is the direction B, so this is plus 10. Alright. How much is that? 1, 2, 3, 4, 5, 6, 10 again, minus of 10. 1, 2, 3, 4, 5. That's minus of 5. B is 0, C is 0. And that's my end point Q. Burgers vector is Q to P. So I got the T vector like this, and I got the B vector like this. See, they are parallel. Opposite direction is opposite, anti-parallel is right. So T and B are facing opposite, but they are parallel. That's the characteristic of the screw dislocation. that B vector and the T vector are parallel to each other. In this case, the angle is 180 degrees, while if they point in the same direction, it is 0 degrees. Likewise, where they point in the same direction, I call them positive screw, and when they are opposite like this, I call them negative screw. So this picture is that of a negative screw dislocation. In positive screw, B and T would point in the same direction. Angle between them is 0 degrees, angle here is 180 degrees. So relationship between B and T I have talked about: 0 degrees, 90 degrees, 180 degrees and 270 degrees. 360 degrees again is the 0 degrees. And these give me the straight line dislocations, screw dislocations and the edge dislocation. Right, then the dislocations in the crystal, well, just to explain that, the symbol of course I have not explained. Symbol we use for positive screw, we use the symbol as a dot and surrounding this a clockwise circuit. That's the symbol we use for positive screw, and in here B and T are parallel. Similarly, in negative screw, the symbol we use is anti-clockwise circuit, and B and T are anti-parallel. This angle is 0 degrees, this angle is 180 degrees. Now let us look at the general or the mixed dislocation. Okay. All right, I come back to my perfect crystal, simple cubic perfect crystal, and this is my slip plane A, B, C, D. Now I cut the bonds in this area of the plane. And let's name this as, this was F point, you remember, and this is my H point. Some curved path inside, and I cut the bonds like that up to there, and then give the front part a push again, or one interplanar spacing. The configuration after doing this, what you will get is, this is the boundary, this is the dislocation line. What you would get is this get pushed, but it's not able to get pushed because beyond this, like in the screw we saw, but here you get a part plane. So configuration here is that of a screw, configuration here is that of an edge, but in between you will find a mixed component, no? Right, very important thing is here, right. So my dislocation line is going like this, coming here. So a T vector in here, if you draw, goes in, and T vector in here comes out. A T vector in here is tangent to the dislocation line there. This is my T vector. That means T vector is not a constant. For a straight line it was, Now it's a curved line, it is not, because at every point it has to be tangent. At this point it is perpendicular to that one. In here it is some other angle. So this is changing, and like this point which I have named as F here, and this was named as H here. If I take this T vector, which way shall I draw the Burger circuit? At this, around this point, clockwise. Good. So what I do is I draw a clockwise circuit. I will not put anything counting. You can count these steps. It's exactly the same way we did earlier. I end up here, I start there, my end point, and this is the Burgers vector. Burgers vector is this from Q to P. Alright, in other words, let me show this. Burgers vector here is this. That's my Burgers vector. Alright. At the F, if I come back, okay, I come back to F. Now I draw it anti-clockwise. So let we start here somewhere else. I start at P prime, I end up at Q prime. You can count your steps. So Burgers vector is this. This is the Burgers vector. This Burgers vector and this Burgers vector. Check that. Direction and magnitude. Same. So Burgers vector of a dislocation line is invariant. Similarly, if you find the Burgers vector at this point, it will be the same. Why is it so? Why the Burgers vector is invariant? Whether I take this shape of the slip part or I take some other shape of the slip part, push which I have given is the same constant. Push is the constant. Direction and magnitude, that's a constant. That's why whatever may be the shape of the boundary between the slit part and the unslit part, this slipped segment or the vector, slip vector by which one part has slipped with respect to the other in the crystal is the same. Everywhere it is the same, it is not changing. T vector of course is changing, because that's a tangent to a dislocation line, and dislocation line need not be a straight line. Therefore, this tangent will keep changing. Is that clear? We shall start from here in the next class.